All right, so as I mentioned when we were defining the traveling salesman problem, we're not often going to look at all the different Hamiltonian cycles because the number of possibilities grows so quickly that it's often impossible. So instead what we do is we look for the smallest upper bound and the largest lower bound of the solutions and know that our solution is somewhere in between. So if we think about this, our solution is going to be greater than the lower bound. So we'll have lower bound is less than or equal to, sorry, the math symbols on Notability are terrible, is less than or equal to our solution, which is less than or equal to the upper bound. And again, we want the greatest lower bound and the least upper bound, because we're trying to squeeze our solution between those two values. If we're super lucky and the lower bound equals upper bound, then we've also found our solution. So that's if we're super lucky, and sometimes the IB is going to contrive problems such that that's the case, because they're going to want to test that you understand what all of these concepts are. So let's start with the upper bound. So we use the nearest neighbor algorithm to find upper bound. Somehow my Notability and computer thinks I'm British. No. Okay, so we want to find the upper bound. And in most problems, you're going to be told what your home city is. So where the traveling salesman starts and ends at. If not, you would have to repeat this algorithm with all the different vertices, and then it's not actually saving you much time. So what this algorithm says is we start at home, and then we go to the closest city that we haven't visited yet. So of course, when you start, that's going to be the city with the least weight. But after you've started, then you're going to go to the next closest city that you haven't been to yet. So we're repeating that until we visit all. And then we go directly home. So this also would have to mean that we have a connection from the last city we visit back to our home base. So if you're having to test out the nearest neighbor algorithm without knowing what your home city is, you would have to make sure that from whatever home city you choose, that there is a Hamiltonian cycle that will get you back to your home city. If not, it's not going to end up being your starting base. So once we've accomplished that, we find the total, and that is your upper bound. All right. We use the deleted vertex algorithm to find the lower bound. And unfortunately for this one, you have to delete each vertex to find the greatest lower bound. So must try all vertices to find greatest lower bound. So what we do is we remove one vertex and find the minimum spanning tree. So we can use one of our previous algorithms to find our minimum spanning tree. After we've found the minimum spanning tree, we have to reconnect the deleted vertex with two edges of least weight that run from the deleted vertex back to any other vertex on the graph. From deleted to any to others. And I've already said with least weight. Okay. So again, we repeat for all vertices. And then we take the largest for your lower bound. Again, we're trying to squeeze our solution between the highest lower bound we can find and the smallest upper bound we can find. All right, in the next video, we're going to look at an example of using these two algorithms on a problem.